All right, good morning, everybody. These are extraordinary times with the VTA strike. The provost is offering, like, not particularly to Uber, but vouchers, right, to help with that. Um, but even I can't fight, you know, local politics of the strike. So I'll try, people can't make it. I'll just try to record the videos. Um, my handwriting is significantly worse for this. And just remind you to, if you ask a question, make sure I repeat the question, right? Um, the program I use doesn't lend itself for me to saving it and giving it to you. All right. So, pretty much everything I have is already in some kind of form of, like, Google Doc or something else. So, for instance, the reason why I like to have everything in Google Notes or Doc is so that you can have it at the end of the semester. When Canvas shuts down, that's it. So for today, we're going to go into more advanced filter structures, which are the ones that are really used. All right. And you're going to use in lab, right? Um, and so, yeah, I have a video. Like, I felt like talking about complex poles, right? I have a video, you can watch that. So sometimes, yeah, why also don't I record a whole lecture? Finding anything anywhere in 75 minutes can be difficult, all right? But just to orient yourself. So here's a first order low pass, design example, right? Which we've talked about, but um, now, yeah, I've called it a first order low pass RC with gain filter design example. So yes, that's the structure, right? But on the exam, you would get, like, design a low pass filter with a cutoff frequency of something and a gain of something else. All right. So yeah, the first thing is we need to design the gain, right? And again, I see R3 and R2, but only one equation for gain, right? So, what's a person to do? Um, anyway, you just solve for one or the other, right? So you have what I sometimes call the feedback and the input. Even though the input is ground, that can help keep track, right? And so in this case, um, I'm saying, well, R3, why did I choose to solve for R3? Well, there's this thing kind of hidden that resistors with Worcestershire sauce, resistors, right? In this context, the 110, 122, 124 context, right, should be around 10 kilo ohms or higher. Now you can kind of get away with 2 kilo ohms, and the reason, right, besides limiting the current, which limits the power, is that the op amps stop working below 2K, right? And you can see it in their data sheet when they'll say open loop gain measured with 2 kilo ohm resistor and it's lower, measured with 10K and it'll be higher. Each company does it slightly differently, but it's there. So rather than solve, oh, I want R2 to be 100K and then divide it and might end up with an input resistor smaller than what I want, I do it the other way, right? And so, yeah, a lot of times for whatever, I don't know, 10K, that's just my favorite. You can have favorites too, just as long as they're greater than 10K. All right. But if on an exam I have said two kilo ohms. What it is when you put it in a circuit, sometimes things go in parallel, and what was 2K is now less than 2K. Right? That's why I start a little bit higher. So I say I choose this, and then I solve for the other. Okay. Now, yeah, a lot of times on exams, I will see that pattern. Great. Um, I can kind of tell people who study together based on the values they choose. I know you're not cheating because I'm staring at you practically the whole time. Okay. Then we have to design the cutoff frequency. Now, in the equation, right? Do I have? I guess I don't. Okay. I don't have the transfer function, but the cutoff frequency in radians is 2 pi whatever is given in hertz. See, that's another thing I love. Find a mistake. So the example must be I want to design a cutoff frequency for a kilohertz. I got to convert it to radians to get my RNC. Now, on the exams, I will give you the cutoff frequency in radians, right? And sometimes, yeah, people they get confused and think it's in frequency. I I think I'm forgiving about that partial credit. Just but really I'm trying to make it easy. Okay. Bodie plots all in radians, right? The transfer functions, of course, are in radians, so that when you solve for RC, well, then it's just RNC. That 2 pi can, that number 6.28 can, you know, add confusion. But yes, the analog wizard from analog devices, every data sheet gives their gain bandwidth. It's all in hertz, right? Bodie plots from LT Spice are in hertz. But anyway, so the thing is what do? We choose the value of the capacitor because there's fewer values. So if you go to, an easy place is electronics, which you have to go there. I don't own stock in them. Oop. But it is just a trip to go to a place where you can feel like, yes, this is where my people are. They're pretty nice. They have like almost anything you need. But there's supposed to be the price list. Apologize, but I got fed up with Adobe products and now nothing. PDFs don't work for me. They got me. So there's a price list, right? 5% resistors, 1% resistors. I'm just going to come down here, surface mount capacitors, right? And you can see 0.5, 1, 2.2. You can kind of see the pattern, right? If you go to 1% resistors, look at how many more choices you get, right? But um, yeah, I'm not. And the 1206 has more choices, but that's only because the they can be larger, right? So the 0.51, 2.7, 4.7, 10, 12, 15, 20, 22, right? That's kind of the pattern that you can get, right? So, and the same with it, and inductors are even more limited, okay? And in one of the notes, I just have a capture of this for the relevant thing, all right? But again, on exams, just choose a value of capacitance first. Right? You don't have to, when I say realistic, no, you just calculate it, right? So anyway, we have one equation and two variables. I choose the value of the capacitor. So C1 equals 100 nanofarads. Now, maybe I already calculated it, or no, actually I made I made a mistake on purpose, okay? I try 100 nanofarads. Okay, I calculate R1. I get 1.6 kiloohms. That's really smaller than the 2K or 10K that I prefer. Um, it's on the verge of working, let's just say. But so I'm gonna I want a bigger resistor. So I see that equation there. So if I drop this by 10, a factor of 10, the resistance will go up by 10 and 16K. There you go. And then I make it an LT spice. That's the generic op amp. There's the Bodhi plot. And I'm measuring the 3 dB point. And notice the gain bandwidth limitation around 100 kilohertz. So remember, for the Bodhi plot of a first order low pass filter, phase goes from 0 to minus 90 and flattens out, right? Now, sure, this slope, if you were to measure it, would still be minus 20 dB per decade, but note right in here, something's happening, and it's a gain bandwidth limitation. Or you could just say that an op amp has poles and zeros. It has poles that are usually out of your range of operation, but you can see what's going on. So that's just like, I just walked you through the design example, right? And then, here is, I think that's just all the files. So yeah, I have all these sample files. It's true. I do now use Colab because you could just take it and you don't have to fiddle faddle. But there's so if you say I need a high pass filter, that that's like the bare minimum you need. And then I'm just showing you how there's the transfer function, right? And this is, then I get the Bodhi plot and then the time domain response. But I thought I had a first order low, first order high. That's just how it works. But the design example is the same, right? You have a cutoff frequency. You just got to switch the capacitors and resistor, and that would be first order.
Can you give us a resistance needs to be more than this value? Like you say that?
I just said, I mean,
I thought I
no, I've said make it bigger than 10. Is that what you want, or do you want, or do you want me to want you to say that on the exam? All right, that got a little crazy.
The stay level. In the test, you're gonna say, oh, the resistance needs to be bigger than this value.
That you need to know. Okay. And the reason why, right, is there is a philosophy here, right? I want to make sure that the tests are meaningful and not just some random thing, right? I can put a random RC network up here and test your mesh and your KVL, right? Or KCL, right? Oh yeah, I'm a great teacher. But the circuit is random. You might never see it, right? So I want to make sure you have the circuits that you will see. And then two, rather than exams, I mean, exams are stressful enough, but if you think it's baloney, well, then that's not good. So what is the idea is that you're about to do your design. what are all the hand calculations and thinking you need to do before you verify an LT spice. Or you're on a job interview and they ask you something and they want to see you think about it. Or you're in a meeting and let's call it the robotics meeting. And yeah, we got a problem with the noise on the sensor. Like, okay, what are we going to do about it? Well, let's see. Do a low pass filter, but how much noise is getting through? Oh, this amount, this dB. I think I need a second order. All right, what are my constraints on the board? Well, you really only have this amount of space. Okay, I can only use one op amp. And that you can think about it in that. Then once you have, so you got to follow that conversation, lead the conversation, and then go verify it and do it. And then the final thing that I can think of today is you guys will be giving the job interview. You'll be the manager. You will be onboarding people and you will come up with a list of questions that you think is important. So you're part of it. So maybe, let's see, within 5 years, so I'm trying to prepare you for that. Oh, and graduate school. That's the final thing, right? Trying to prepare you for graduate work, right? But that's maybe a little more than what you wanted. But that's why I want you to know roughly, yeah, around better than 10K. Like why the cheat sheet doesn't have a lot of stuff. There's things you just got to have in working memory. Any questions? Continue that conversation, or do you want me to? Okay. And so, but really, if it's, I like above 10, but the data sheets are like 2K. So if it's around 2K, all right. But if it's below that, I've seen circuits not work because the op amp can't drive the current. So then that's not realistic. That being said, people tend to knock this problem out of the park. Okay. So now I'm just going to go back into the review machine here. Whatever the thought bubble. So let's just do a low pass. And I'm just going to say F naught because that is how you'll get it. So I have my magnitude and somebody said that's the cutoff frequency. But as you know, right, the signal gets multiplied by as the frequency goes up, the signal gets multiplied by a smaller and smaller scaling coefficient to get rid of noise, right? But let's say you have a signal here, right? And I'm just going to say, at that point, it's gone down. That's minus 20 dB, right? So it's scaled by what? 10 to the minus 1. So whatever comes in, it gets multiplied by 0.1. But what if 0.1 is still too big? Like let's say it's a noise and you can still hear it and you got to get rid of it more. I'll just throw it out there. What is an option that I can do? Sorry. Okay. All right. It's a good answer. I just want to hear the words everybody's. So you're right. I just want to hear what everyone else was going to say. Yep, that could work too. But again, there might be a reason why it's that high. But yeah, it's something that can. Did anybody else have anything? Okay, so right, if I shift this back, but many times, whoop, so let's call that minus 40 dB, right? So at that same point, I would have 10 to the minus 40 divided by 10, which is what, 0.00.01. Now, I'm sorry, that's what I say. I have a hard time drawing with this thing. All right. So now I've reduced it. How do I get the second order? Well, in some ways, you've already started to do this. So here's first order, and I'm just going to use a buffer, okay? No gain. You need this because as soon as I hook up a load, it affects the resistance, and then your cutoff frequency is off. That's, really what it does is it isolates whatever you're hooking up from there. All right, I want a second order. Well, just put it there, right? And the transfer function would be, sorry, I got to draw it over here. 1 over R1 C1 times S plus 1 over R1 C1 times 1 over R2 C2 times 1 over S plus R2 C2. Okay. Now, what if I just think, like you're the person who has to buy these parts or pay for the parts, right? What did I just do to get that second order? Yeah, I added an extra op amp. And I know we're talking about multi-billion-dollar companies, but sometimes when and they might have multi-billion-dollar budgets, but you, the design engineer, do not have that. Okay. Sometimes, and especially if you're working in toys, oh, the profit margins are really tiny, right? Anybody remember the old hoverboards? Everybody remember the old hoverboards catching on fire? Well, there's a $3 part that'll prevent that from linear technology. Yeah, it's all has okay. You're gonna get me monologuing. No, but what I'm saying is this would be more EE136, and when you're charging a lithium ion battery, it's there's hydrogen coming in and out of that, and you have to be very careful. So you need a part to regulate how it charges up. Now, do you need that every day? No. Will you need it on every lithium ion battery? No, but if you make enough of them without that part, the garage across the train tracks from my house will catch on fire. Or Moss Landing, which I don't know what happened there. But that's a $3 part on a $50 toy. So I've added that. So let's see if we can get rid of it. Okay. Well, hey, here's an idea. I see two capacitors. And notice you can't, this resistor here makes it so that I can't put them in parallel or put them in series. So it's second order. Okay. And hey, just like I did before, I just stacked them. So you might think, and I'm going to just come back. Uh, oh, I'm already running snag. So you see this equation, 1 over RC1, right? The poles are separate, everything is fine, it's relatively easy to design. You might think that you can use that equation here. Oh no, that is the opposite, right? I have that current, and that current, and that current, and I have that. And notice, this voltage here is going to depend on what's going through here. It's actually 2 nodes that you have to solve for. This filter can never have complex. Second order loop. Okay. Sorry, I'm talking to myself. So that's what we have here, except I've used impedances, right? I assign the current directions, right? And I'm doing it on the, and the thing is this is like a really hard circuit to analyze. I got to be well rested and in a good mood to be able to get the right answer. Oh, it's the same one. This is, I'll come. This is the same. The other second order?
Yeah.
Yeah. You're right. You're right. Sorry.
Yeah.
Oh, no, because I can't draw at the same time. What it is there's a lot of times you don't want to use 1 over R2C2. You want to use omega naught, and then so yeah, even you can be prone. But thanks for pointing that out. Okay. Sorry if I was ignoring. Come back here. Okay. So now it's the same thing, and I'm just showing you how to design it, and even how to use SymPy to do the algebra. So what I'm doing is I'm checking my work the whole time, and it gets a little hairy, right? And that's not what today is really about. But in the end, I have C1, C2, R1, R2, and they're in every term. I need to solve for the poles. So this is just like a second order circuit, except R2 is a scalar of, this probably should be R1. And C2 is a scalar of C1. Then I can go, because I want to design a circuit with a 1 cutoff frequency, but I got 4 variables. So what I do is I make one capacitor a ratio of the other, and one resistor a ratio of the other, but still, okay? And this is me proving that that circuit cannot be underdamped. I'm not going to go through that today. You can read that on your own. But down here, you'll see I have to kind of guess. I say M should equal 1, that ratio. Okay, if that's true, R1 is a kilo ohm and C1 is this, then the poles are this, and I'm just kind of, seeing where it goes. Now, at the end of the day, you can make a low pass filter, and it works, all right? I don't really do a design example per se because well, that's used for like band pass. It's not used really for low pass. Okay. And so now I need to go back to the Bodie plot. Okay. So that's first order. And then what I'm going to do is draw the real Bodie plot. And it's minus 3 dB, okay? First order. The filter that I just, the second order filter will now have a sharper Bodie plot. But now it has 6 dB. A third order filter would be minus 9. And it just makes it really, so yeah, over here, it's still minus 40 dB, but you have this, you really want the bandwidth to be flat as close as you can to the cutoff frequency. But this is really what's happening is I set the cutoff frequency, the higher the order, actually it starts attenuating into the spot that I don't want. And that's because the best I can do this, and that's really all that math, was that the best is critically damped. Right? Which means there's 2 repeated poles minus 6 dB. And also I'm showing that if I choose certain ratios, I can easily design this. All right. But the problem with this circuit is, and I am going to skip back to the math. What's the transfer function? Okay. Let me just zoom in here. So the transfer function is this, right? But A1 is that. And A2 is this. So when I want to do over under critically damped, right, this A1 is really the B, and that A2 is the C. So when I come down, right here, greater than 1 damping coefficient. So this whole 2 zeta omega naught would be A2, no, A1, no, A2. I gotta look it up. Yeah. These 3 terms are really A1. That term is really A2. And what happens is, notice in A1, R1C1 is there, C2 is there, and R2 is there. Notice in A2, all 4 terms are there. Let me go back here. All right. So just a quick thing with, here's an RLC circuit, right? And we have S squared plus R over L S plus 1 over LC. Well, notice plus or minus B squared minus 4AC. Well, notice here L is in C and it's in B, but R is only in B and the capacitance value is only there. That means I can independently tune it. So if I set LC, I can find an R to give me over, under, or critically damped. But notice here, R1, C1, R2, C2 are in both of these constants. So you can't independently tune them, right? And in case we forgot, we wanted a second order filter, but we wanted one op amp, right? And so some things are best just to read on your own, right? I can be talking about it and, you just have to kind of go at your own pace. The problem is the reason why this is so is it comes about from here is that's to ground. All right. If it were somewhere else, it would not be in the equation. Okay. So somebody had this great idea. I still have four impedances, right? But notice you can kind of see it. Actually, I I misspoke a little bit. Let me come back here. I was saying the problem was here. The problem is this one, or all right, is that because that's both tied to ground, all four of these are in every constant. So if we come back to here, notice these two are still, that kind of looks the same, but Z3, which would have been to ground, is now going to V out. And it's actually positive feedback. Normally, everything we've been doing is negative feedback. All right. And because of that switch, and this is just generic impedances, right? Uh, okay. So here's that equation. Here's omega naught squared. What's omega naught? It's 1 over the square root of, there's R1, 2, all the R's and C's are in this term. 2 alpha, right? 2 alpha. What's in that? Well, there's C1, R1, R2, R1 and R2 are there in C1, but C2 is not. It's here in this part, but not here. Now we can solve for things much easier. And then, yeah, they do this trick where rather than have two resistors and two capacitors, you have something called R and C. R1 is a scale factor times the R, right? So I choose R, let's say it's a kilo ohm, and M is 2. R1 is 2 times that, and then R2 would be divided by 2. Same with this. And it makes it a lot easier. And when you use the analog tool, you might notice that, hey, it always seems this is bigger than this by a certain amount, right? This is where it comes from, all right? I don't use Q so much, and then they do a design exam, all right? If you come back to the notes, Sallen and Key, let's see which GitHub, okay? I do it all. I repeat Wikipedia, all right? But I actually figured out why. They don't say why those scale constants are the way they are, right? I kind of go through it. And then in the end, there's the low pass, and there is the step response. Okay. Even if you're reading the notes ahead of time, like you're supposed to, right? Which is how you handle grad school, right? I probably lost you at this point. Or I haven't lost you and you're really scared about the exam. Okay. This is not on the exam. Okay. It can't be. Unless I say, you're going to bring all your design tools, and the question is design a second order low pass. Everybody gets a different spec, and you design it and you prove it in LT Spice, right? Um, well, no, that could be one question, and then I'll ask something else, right? But so you might say, well, professor, don't waste my time. I'm really busy here with VTA and 112, right? Why are you doing that? Well, because you're going to do it in lab, right? And we don't really have a lot of time for theory. Lab should be due, not like talking. Yeah, exactly. So that's why I've taken that time. And and what I found is like, oh, you can use that analog wizard and get the numbers and all that. But really, if like this, some of you, yeah, you're gonna enjoy, let's say, the 118 side of things better. This might not be your thing. But if it is gonna be your thing, the idea, like, well, where did this circuit come from? Right? It's what you see in the data sheet, like, you know, that big book I handed out of stuff. Oh, well, you use positive feedback and you get the pole you want. Huh? That's all they say. Like, you should know. And so, really, just think about it. This is what really happened, I think, although it's not in any history. You have a first order, then somebody invented an op amp, right? Which used to be done with tubes, okay? Then somebody wanted a better filter, and they did this, right? But now they needed to add another one. Okay. Now remember, those op amps were really expensive and big. I mean, they're tubes, right? So then somebody thought, well, can we do this? Or maybe this circuit came first. I don't know, right? But you can't get that filter response you want. And then somebody, Sallen and Key, for example, said, you know, if I could somehow change that, so now what I'm going to draw it a little bit differently, okay? And keep this. Well, here's this part right here, right? Here's my first order. Here's my first circuit. RC, that's my thing. That's not mine, right? But instead of this, boom, Sallen and Key, which is great. It can go from rail, it can, like if you only have a positive rail and you're trying to filter a positive signal, you don't have to deal anything with it. But it has gain bandwidth issues with this positive feedback loop. All right, and you'll see it when you do it in lab because do an RLC circuit, do this, do Sallen and Key, and then do multiple feedback. Let's go to our old friend. Where's the old friend? Open this macro models examples. Okay. So in this circuit, I know I make a lot of crappy jokes, but laughing when I'm not is like, yeah, it worries me. Notice one, two, three, wait, one, two, three resistors, two capacitors. Okay, so there's some more parts, right? But this is, notice how the input, how it's coming in. It's coming in on the inverting side. It still has this positive feedback, and so does this, right? And you might wonder why 5 parts versus 4. And now that it's inverting, I need to have -5 volts. But they've done a trick to where you can still make it a positive supply, right? And so, yeah, I can't grab it because I'm using Snagit right now. And now it comes out positive because this whole thing has a negative transfer function. This has a negative transfer function, and it's a fourth order. And I'll show you that in a second where that comes from, right? Good question. Is because if it came, all right, here, C1 would be negative, right? That's negative feedback. But because it's coming out over here, it becomes positive. It's not obvious. I can only do it, I can solve the math, and sometimes I still don't see why. That's why somebody just had this, I think, a flash of insight, said, oh, that's what it is. So, but I guess, here, right, I came around the bottom to show you how similar it was to the circuit. But really, it's normally drawn the other way. You come here to here. Where's, see, you come from here to here, right? And now, what that means is if this voltage gets higher, then that voltage gets higher as it's added back in, okay? Um, yeah, does that help? But the negative is here because you see that's a subtractor, right? But then, yeah, it just works out that way. But you can see that the difference is the RC is on the positive side. You can see the differences. And what I found is like, why is it seem to be worth it? Is that when I ran it head to head, that the gain bandwidth issues were better. And that it seems that this here, right, is a buffer, right? And for whatever reasons, this buffer, when it stops working, the whole circuit stops working. And the fact that that's a buffer causes this circuit to stop working or have unintended consequences than having again, this is a non-inverting, this is from here to here, right? It's an inverting amplifier, right? And with a capacitor in the feedback loop, it just has it works for a longer period of time, okay? Each time I give this lecture, I learn a little bit more, okay? Because I didn't, well, I've I used it later in my career. As an undergrad, we didn't really do that. I wasn't I was in device physics and that was more my senior project. Okay. But so now when you go to wizard, filter design tool. Uh, I'm going to make a low pass. Okay. And it does, what it is, you don't give it the transfer function. You kind of have to say, well, I want the gain to be a certain value, and I want it to be minus 3 dB here. So you're telling it the cutoff frequency. Now, I would like it if I could just say, oh, I want a slope of minus 40 or, as, right? But no, they give you what is known as the stop band. Like I want minus 4 dB to be at 40K. How would I make this a higher order circuit? Oh, I would just want it to be there. And then there's choices. Fewest number of op amps. Okay. Can you see the word there when I'm wiggling it back and forth? Okay. So over here is something called a Chebyshev filter, right? Which uses the fewest number of op amps. Then it switches to Butterworth, which is the one we're actually kind of using a lot, where the damping coefficient is 0.707. Then there's Butterworth Bessel, which is another kind of filter, and then pure Bessel. And it's all has to do with the constants in the denominator. So I'm going to keep it Butterworth, okay? But actually, so yeah. So if I say it doesn't have to be perfectly flat, I can get away with less things, right? And if I like, well, I can't, but I need it to be fast. Oh, it just says, don't, no, that ain't gonna work for you, my friend. There we go. But maybe, it's not this curve that I'd been expecting, right? So I'm just putting it in the middle. All right. I have friends over there, so I'll accept the cookies. All right, components. Uh, Interesting. It added a pole here, so it's actually 1, 2, 3, 4, 5. It's a seventh order filter, and it added one regular, traditional filter that we've been talking about, right? But then here I have resistor, 2 resistors. It's drawn upside down to the way I draw it, but this is Sallen and Key, Sallen and Key, Sallen and Key for low power. I don't know. What about voltage range? Does that change it? But there's some, oh, compensate for gain bandwidth. Okay. But there's something where it's supposed to, I'm supposed to be able to choose. I want to choose. Okay. Op amp implementation, buffered RC. All right, stage D, Sallen and Key or multiple feedback. Sallen and Key or multiple feedback. No, I'm just making this up, right? But then you should, so tolerances. So now, like, what resistor should you buy? Next steps. It's supposed to be a Bodhi plot here. Anyway, you can download the spice deck. I thought it. See, that's definitely a Bodhi plot. Anyway, it should do the Bodie plot for you. Okay. Oh, view circuit. How about magnitude? Bam. And notice it's giving you like the possible tolerances based on the parts. So if you measure anything within that, then the circuit is working. And if you're measuring outside of it, like I was describing the other day, well, then it's, something's not right. Oh, yeah, Joel.
Can you go back to the type and change it so it's a minimum number of op amps and it's back?
Oh, no, I only used my one for today. All right, so fewest stages? Okay. So then it gives you the components. Where's circuit?
Oh shit. Oh, only 3.
Right.
Still.
And it's what? See, this capacitor is in the feedback loop. That's the multiple feedback. All right. I can go back stage B. All right. And then 2, RC sizing. That's, oh, maybe that makes the capacitor smaller. Is that what's happening? And now the capacitor is bigger? Or something. Anyway, you can play with it. This thing, it gives you almost a different part for almost everything, right? But, you're designing something. Yeah. In the lab manual, though, I show you how to set the spec so that you will get, like if it's, you'll get, I think, 4th order on purpose, right? Or whatever order you want. I show you how to set the spec so it does what you want it to do rather than guessing. Because, yeah, having an op amp just to have one pole, it's kind of a waste. So you should get like 2 poles per op amp, I think. But, it's like maybe there's a reason for it. That's why they let you do it. Okay. But that is, and then you're going to use those filters for the final project, a pulse width modulated DAC, right? Digital to analog converter, which can go in your resume, which when I write a letter of recommendation, I go find your project. I'm like, oh, they did a pulse width modulated DAC with 7-bit resolution at such and such. That's why in that abstract, you'd say exactly what you did. I can go back, find it, and then write, cut, paste. They did this for me. See? Now that's a lot, right? When we come back from spring break, right, we'll have a practice exam. And then on the Wednesday, we will have the exam. But everything that I've created that I don't think is a distraction, I've created a lot of things, but I'm like, maybe later, right? It's here. So midterm review, sample exam, there's another sample exam, and then here's like link to previous exam solutions. It's already there, right? Well, an onion cat. So, there's like a digital design contest, and there's also this, you can make a digital circuit, have it made for you, right? For like 50 bucks. And then, yeah, about 200 for the board to test it, which I have. Um, it's pretty slick. Well, what somebody did for their VGA demo was to have, I think it's, I think they made a video. So let's see, let's go to GitHub, read the documentation. I don't know. I thought it would play. Anyway, people wrote 118. All right, you're all using an FPGA. Who's using the FPGA in 118 now? So that is Verilog, right? You're using Verilog, right? Well, they created the circuit in Verilog to run that, and the rainbow kind of goes and the stars blink. Okay. Now, yeah, I ordered some FPGA boards that then you can plug into the monitor so that, yeah, if people wanted to do it on the FPGA project, you could just port it to that board and all of that. So I did not know what that is, but when I was showing a group of students about this thing, they saw, I was just scrolling through projects, and they saw Nyan Cat, and they went crazy. So yeah, I know about the Incredibles and this. Okay. So yeah, you know, kind of stopped. My kids got older. We don't watch Pixar anymore. So Incredibles is the last thing I remember. And now night. So yeah, see you guys lit up. All right. That being said, oh, and that is like a research thing. I have research groups. People can work on that. I'm actually trying to get Professor Kim to be able to kind of do that thing over the summer with students for transfer students. Actually, they didn't do that, but they did do tiny tape out over the summer. Did anybody do that for transfer? No. Okay.
Transfers, they said.
It was Summer Bridge, Exceed, and you had a project. It was all online.
That's why.
No, this was only transfers. I want it for people who were here. Anyway, let's come back to here. So hopefully that you can, and yeah, it's like, okay, hey, easy circuit, a little bit better, right? Has advantages, disadvantages, much more flexible, but you have to be careful. And then the multiple feedback one, same thing. But I'm not going to ask you to derive these circuits on an exam because it's something that, all right, this is my project or my senior project. I really need to know this in and out. Okay, then you should actually make my Colab code in SymPy and you do it, right? You'll learn a lot more than just reading my code. But that being said, that's the big deal. Um, I'll just throw it open to questions on anything.
I had a question about that restart circuit you were doing Monday for Signal Plus.
There was 3 parts.
Where you got the advanced summary.
You know what? Oh, okay. Yeah. 'Cause usually these two represent the same line, right? That's a good question. I think I know where you're headed. Okay. So, all right. So we talked about signal flow, and this is how I first introduced it to you. And this was, and I'm going to draw it the way that more closely matches. Okay. And so this is the signal flow graph for a op amp based circuit. All right. And really, ideally, this is the gain. Now then I did more generic. I have a positive input and I have H, okay, which could be an op amp circuit. And then rather than just a scale, it could be a function of S, right? So if I say, uh, I'm just making up a different example. I'm just going to say this is 10, okay? I'm going to make G 1 over S. Well, how do I get 10? Well, that circuit is probably in there. But am I going to substitute this whole transfer thing into here? No, that'd be too complicated. I'm just going to say 10 because I assume everything is ideal. Then when I build it and simulate it and it's not, well, I know it's gain bandwidth. And then here, right, it's 1 over S. But the only thing that does that easily is this, minus 1 over S. Capacitances and resistances all selected to make 10 and 1 over S. So now, right, I have out equals in H minus out G H. Out in H 1 plus GH, which we've done a fair amount of times. All right. But yes, that 10 really has this inside of it. This has another transfer function that is much more complicated, but I do have it in the notes. All right. So now I just have to do, I have 10, 1 plus 10 divided by S. That's not the right format, so I multiply through by S, and so I get S10, S10. Uh-oh. You know, it's hanging. So I multiply it by through, right? I get S times 10, and then I get S plus 10. And so I get a high pass filter that has actually a gain of, I said high pass with a gain of 10 and a cutoff of 10 radians per second. But this two op amp things, so when I go and put the summer and use the summer op amp, that has gain bandwidth, it has a transfer function. The H has a transfer function with an op amp, and the G has a transfer function with an op amp, which you could do and keep it all there, right? You couldn't, it'd be hard to design with it, but then it would match your op amp a lot better, right? Um, but really, you put it together, ideal, and then see whether it kind of works or not, at least at this level.
So for the second homework where the output is in the middle of the H.
Right. You're going to have to look, what it is the output comes before the H, and you do it. And I did it last time, and there should be case studies, but you just see now my machine's hung. But just take out and put it on that node. What would out equal? Out would equal in. And then it would be minus out times H times G. And so what you would get is instead of the H on top, right, it would just be 1 divided by 1 plus GH. And again, I'm sorry, hung up, I hope. Oh boy. Want this video.